Are you ready to explode your mind? Welcome to the future of creation.
Hey everyone, welcome back. I am absolutely pumped for today's explainer because we're going on a seriously fascinating journey. We're going to map out the exact anatomy of the modern industrial network. We'll start way up at the macro scale of massive factory-wide communications and zoom all the way down to the micro level, looking at the actual physical hardware and the tracking codes that hold the whole shebang together. If you've ever wondered how modern factories, robotics, and automated power plants actually keep running without just collapsing under their own complexity, well, you are definitely in the right place. So let me throw a really provocative question at you right out of the gate. How exactly do you build a network that is lightning fast, but also universally safe? Historically, in the world of high-stakes automation, we're talking spinning robotic arms, power plants, massive packaging lines, engineers have always had to compromise. If you wanted absolute fail-safe security, you had to slow things way down or run completely separate, incredibly expensive, redundant networks. It was basically a forced choice between speed and safety. But as we'll see today, thanks to some truly brilliant engineering, that compromise is officially a thing of the past. Okay, let's dive into this. Here is our roadmap for today. First up, we'll look at the Ethercat ecosystem. Second, we'll get into FSOE and the black channel. And finally, we'll wrap up with the Beckhoff identification code.
All right, Section 1, the Ethercat ecosystem.
When it comes to the industrial world, this technology has rapidly become the undeniable engineer's choice for automation. And there are 6 major reasons why Ethercat is so dominant right now. First off, it delivers exceptional performance. We're talking nanosecond synchronization here. Second, it has a highly flexible topology, letting you connect up to 65,535 devices on a single network using line, tree, star, or bus layouts. Third, it's a super versatile, open global standard. Fourth, it's surprisingly low cost because it completely eliminates the need for expensive network switches. Fifth, it's really easy to set up and incredibly robust, with automatic addressing and built-in fault finding. And finally, number 6, it has lean, lightning-fast integrated safety built directly into the bus, which we're going to dig into in just a minute. And this brilliantly illustrates the real secret sauce of Ethercat. How does it get that insane performance without those pricey switches? It's all about dynamic data processing. So instead of sending a data package to a device, waiting for it to open it, read it, and then reply, an Ethercat network processes data completely on the fly. Every single node on the network reads the data addressed to it and instantly writes its own data back into the frame, all while that frame is actively moving downstream. It's literally like a high-speed train where the passengers are boarding and disembarking without the train ever actually stopping at the station. Pretty cool, right? Moving right along, Section 2, FSOE and the black channel. So let's transition from those broader network benefits and do a deep dive on that last key advantage we mentioned, integrated safety. To really understand fail-safe over Ethercat, or FSOE, you first have to understand the black channel approach. Now, in older, traditional safety systems, every single wire, switch, and controller had to be heavily safety rated. But the black channel approach, it flips that logic completely on its head. It just assumes the underlying communication network is totally untrusted. Think of your standard network cable as a dumb, blind, and totally unreliable courier. But you give that untrusted courier a highly locked, tamper-proof briefcase. Because the network itself isn't trusted, the safety of the entire system relies purely on the secure endpoints verifying that data before anything is allowed to operate. Now, what's really interesting about this slide is the software architecture. Look at how the standard applications and the safety applications are sharing the exact same communication interface. Because of that tamper-proof briefcase we just talked about, which is technically called the SOE safety container, you don't need a separate dedicated network just for your emergency stops or light curtains. Standard motor speeds and highly critical safety data actually travel together securely down the exact same physical Ethernet cable. So what makes the safety container so bulletproof that it achieves SIL 3 compliance, which is a massive industrial safety rating, by the way? It uses 4 tightly layered safeguards. First, a hard-coded connection ID ensures an emergency stop meant for one specific robot isn't accidentally executed by another. Second, sequential numbering instantly catches if a network glitch drops or duplicates any data. Third, inside sits the actual safety process data payload. And finally, it's all protected by a CRC, or cyclic redundancy check. This is a mathematical checksum so incredibly strict that if even a single binary 0 or 1 flips because of electrical interference, the whole packet is immediately rejected. No questions asked. And in real time, this whole transaction happens in an absolute flash. First, the safety PLC generates the logic, adds the security elements, and locks the container. Next, the standard PLC packs it up and sends it blazing down the wire. Upon reception, the terminal instantly extracts the container, hands it straight to a dedicated safety microcontroller, and meticulously verifies all 4 safeguards. If everything matches perfectly, the machine runs. But if even one check fails, say a sequence number is off, or the CRC doesn't perfectly match, the output is instantly killed, preventing a catastrophic industrial accident in a matter of nanoseconds. Okay, on to our last stop, Section 3, the Beckhoff identification code. Let's move to the physical side and see how this all builds together. Because honestly, all of this lightning-fast software and complex routing is totally useless if you can't properly track, maintain, and identify the physical hardware components themselves. And that is exactly where the Beckhoff identification code, or BIC, comes into play. If you look at the code stamped directly onto the hardware here, you realize the entire virtual macro network is ultimately anchored by these perfectly tracked physical devices. For the logistics experts and engineers tuning in, you'll appreciate that these specifications are incredibly strict. This isn't just your average barcode. It utilizes a highly resilient data matrix code format tied to the rigid ANSI MH10.8.2 2016. Whether you scan the packaging or scan the product itself, this code guarantees flawlessly streamlined handling and product management across a massive facility. It ensures every single piece of hardware is exactly what and where it needs to be. Embedded right within that big sheet is a crucial element called the BTN, or the Beckhoff traceability number. This is an 8-character unique serial number. And what's absolutely brilliant about the BTN is that it's designed to replace all those older, fragmented serial number systems, like messy batch designations or legacy safety serials. It completely standardizes tracking across every single component in your architecture. It essentially ensures that the physical reality of your factory floor is just as seamlessly organized as your Ethercat network data. And that brings us to the end of today's journey. We've zoomed out to the sprawling 65,000 device capabilities of the Ethercat ecosystem. We navigated the brilliant software protections of the FSOE Black Channel, and we zoomed all the way back down to the 8-character traceability codes printed right on the physical terminals. So I want to leave you with this final thought. Based on this macro to micro journey we just took, are you leaving crucial efficiency and safety on the table in your own industrial network architecture? Take a hard look at your systems. There might just be a lightning-fast, universally safe upgrade waiting for you. Thank you so much for learning with me today, and I'll catch you on the next Explainer.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.